Have you ever wondered what makes your smartwatch tick? Or how your coffee machine knows exactly how to brew your drink? Or how a car's engine runs so perfectly? Well, the answer is a tiny, hidden computer, a microcontroller. And today, we're going to pull back the curtain on these microscopic brains that literally power our world.
So here's our game plan. We'll start by seeing just how ridiculously common these things are. Then we'll take a tour of the silicon brain itself. After that, we'll dive into how we bring them to life with code, figure out the art of picking the perfect one for a project, and finally, we'll go over some common mistakes so you can avoid them.
All right, let's jump right into Section 1, the tiny computer everywhere. To really get what these are all about, you first have to understand just how widespread they are. And trust me, it's staggering.
So, what's the common thread between a toaster, a car, and a fitness tracker? You guessed it, a microcontroller. But here's the key. These aren't like the powerful processors in your laptop that can do a million things at once. Nope, these are specialists. They are tiny, super efficient computers designed to do just one or two jobs, and to do them with absolute, rock-solid reliability.
And this really gets to the heart of it. An MCU, a microcontroller unit, isn't just a processor. It's an entire computer system on one single chip. It's got the brain, it's got the memory, and it's got the senses to interact with the world around it, all bundled together to be incredibly cheap and dependable for whatever task it's built for.
Okay, so we know what they are. Now for the really fun part. Let's pop the hood and take a look inside. What actually makes one of these things tick?
You know, at its core, every microcontroller is made of just a few key parts. You have the CPU, that's the brain, doing all the thinking. You've got memory, for storing the rules and remembering what it's doing. And, crucially, you have peripherals. Think of these as the chip's eyes, ears, and hands, letting it interact with a physical world. Slap on some circuits to keep time and handle startups, and boom, you have a self-contained computer. Now let's zoom in on that CPU brain for a second, because there's a really important design choice here. Most MCUs use what's called a RISC architecture. So why? Well, it's all about predictability. RISC uses simple instructions, which means you know exactly how long an operation will take. When you're controlling something like a car's braking system, you need to know it will take precisely 5 microseconds, not somewhere between 4 and 10. RISC delivers that perfect timing every single time.
And that need for speed continues with how they handle memory. MCUs almost always use a Harvard architecture. The easiest way to think about it is like having 2 separate highways into the city. One is just for fetching instructions, the what to do part, and the other is for grabbing the data to do it with. This lets the CPU do both at the same time, which is a massive performance boost for real-time control. No traffic jams.
So where does everything actually live? Well, an MCU is smart about it. It uses different types of memory for different jobs. Flash memory is like the permanent library where the main program, the rulebook, is stored. SRAM is the super-fast workbench where all the active calculations happen, but it gets wiped clean when you turn the power off. And EEPROM? That's like a tiny little notepad for saving crucial settings, like your Wi-Fi password, that need to be remembered even when the device is unplugged.
Okay, this part is so important. Peripherals are how the MCU actually connects to the outside world. An analog-to-digital converter, or ADC, lets it read a smooth, real-world value, like from a temperature sensor. Pulse width modulation, or PWM, lets it do things like precisely control the brightness of a light. You could say these are the MCU's senses and its voice.
Okay, we've got the hardware down, but a chunk of silicon on its own is, well, just a rock. Now we have to talk about the software. How do we actually bring this chip to life? The instant you power something on, this whole sequence happens in the blink of an eye. The chip resets, it looks up where its instructions start, it quickly sets up its internal clocks and memory, and then bam, it jumps right to the main code that a developer wrote. It's this precise, lightning-fast dance that kicks everything off perfectly every single time. Now, when developers write that code, they hit a major fork in the road. You can go bare metal, which means controlling the hardware directly. It's super efficient, perfect for simple timing-critical jobs. Or, for more complex stuff, you use a real-time operating system, an RTOS. Think of it like a little traffic cop inside the chip, expertly juggling tasks like reading sensors and updating a display, all without ever missing a beat. Now, for anything that runs on a battery, like your fitness tracker, power is absolutely everything. The entire design philosophy is simple. Be as lazy as possible. Seriously, that means slowing down the internal clock, shutting off any parts of the chip that aren't being used, and putting the whole thing into a deep sleep. It only wakes up for a fraction of a second when it absolutely has to do something. So with literally thousands of different MCUs out there,
How in the world do engineers pick the right one for the job? Well, it all comes down to the art of the trade-off.
You'd probably think it's all about raw speed, right? But check this out. A lot of the time, the most important thing is just having the right set of peripherals. Does it have what you need to talk to a specific sensor? Does it have USB? After you nail that down, then you start balancing power, cost, and performance to fit the project. It's a puzzle.
And here's a number that might really surprise you. A good ecosystem, which means great tools, software libraries, and examples from the manufacturer, can save over 75% of development time. Yeah, you heard that right. Choosing a chip that's well supported is just as critical as the hardware itself. It's the difference between starting from scratch and getting a massive head start.
All right, let's wrap this up with some hard-won wisdom. What are some of the common traps that even experienced engineers can fall into when they're working with these tiny computers?
On the hardware side, it's the little things that will cause you the biggest headaches. Forgetting a tiny, dirt-cheap capacitor can create electrical noise that makes the chip act erratically. A sloppy layout for the clock crystal, which is basically the MCU's pacemaker, can throw off all its timing. These small oversights can lead to random crashes that are an absolute nightmare to debug.
And in the software, some classic mistakes include using up all your temporary workbench memory. That's called a stack overflow. Or writing a piece of code that hogs the processor and makes it miss other important events. The goal is to always be efficient and responsive, never letting the chip get stuck just waiting around in some useless loop.
This quote highlights something that's not technical at all, but it is absolutely critical. Choosing a part that you can't actually buy in large numbers, or one that might get discontinued next year, can completely kill a product. The supply chain is a huge piece of the puzzle you just can't afford to ignore.
So there you have it, the grand tour of the microcontroller, the unsung hero of our modern world. It's an entire computer perfectly tuned for control, efficiency, and reliability. Now that you know what's going on inside, the only question left is, what amazing thing would you build with one?